Hello everyone, welcome to the channel Statistica Hub. So in previous lecture we have studied the concept of basis and dimension. In this lecture we will continue it further, basis and dimension topic. So we want our basis vectors to be linearly independent to each other because we want these vectors to generate the unique information. And if these vectors are linearly dependent, okay, they will not generate the unique information. Okay, now if we'll see this in the terms of vector subspace, then a vector subspace has more than one basis. A vector subspace has more than one basis. Let's see it how. So if I have a basis vector set of basis vector as let's say a1, a2 to ak. This is the my basis vectors for subspace S. Okay, this is the subspace for subspace S. Okay, and if there exists any scalar, let's say gamma, which is not equals to 0, and if there exists any scalar gamma, then gamma a1, a2 to ak is also a basis for subspace S. For subspace S. Let's see it how. So we have already said that A1, A2 to AK is the basis. So if I write it in the linear combination as for the scalars alpha i's as alpha 1, A1, alpha i's, which are scalars, as alpha 1, A1, alpha 2, A2 to alpha k, AK, which is equals to 0. Now as these are the basis vector, these would be linearly independent, and we know that these vectors are linearly independent, so the scalars that all the alpha i's would be 0 as these are linearly independent. Okay, now if I check the linearly independent independency for these vectors, then what would be the linearly independent independency for these vectors for scalars alpha i's? Let's write it in the linear combination as gamma a1 alpha 1 plus a2 alpha 2 to ak alpha k equals to 0. And here we have got all the alpha is equals to 0. Okay, all the alpha is equals to 0. So gamma a1 equals to 0. Sorry, gamma alpha 1 equals to 0. Alpha 2 equals to 0. Alpha 3 equals to 0, and all the alpha k to alpha k equals to 0. So all the alpha k is equals to 0 from this, and if I multiply any scalar to the 0, it would also give me the 0. Okay, so from this I got that this set of vectors are also linearly independent, that gamma a1 a2 to ak are linearly independent because all the scalars are 0. Okay, now if there exists a vector a, if there exists a vector a from the subspace S, okay, then in the basis we can represent any vector which belong to the subspace S in the linear combination of the basis vectors. So for this set of basis vectors, I can represent this vector into the linear combination of this basis for the scalars. Let's say lambda 1, lambda is as lambda 1 a1 plus lambda 2 a2 to lambda k ak. Okay, now in the first term, if I multiply and divide the term gamma, which is the scalar, it would give me alpha 1 a1 upon gamma into gamma plus alpha 2, sorry, lambda 2 lambda k ak. Okay, now from this we can see that a1 gamma a1 gamma, that a vector can also be written in the linear combination of gamma a1 gamma a1 a2 to ak. So what did we get? That gamma a1 a2 to ak, this vector A can also be written in the linear combination of this new basis of this vector of these vectors. Okay, so from this we got that as these vectors are linearly independent and these can represent the vector A into the unique linear combination. So these near this set of vectors gamma A1 A2 to AK will form the new basis. This is the new basis for subspace S. For subspace S. Okay, and we can also see it like this, as we know that a plane becomes a vector space. Let's say this is the plane. A plane becomes a vector space if we fix the origin at any point in the plane. Okay, if I fix the origin here, then this would become a plane, because we can define then vector addition and scalar multiplication very easily. Because for vector space I have the zero vector, so for that I have to pass the plane to the origin, and after that we can define vector addition and scalar multiplication easily. So okay, so for the plane to be a vector space we have to fix the origin at any point, so this would become the vector space. Okay, now if I draw a plane like this, if there's a plane like with the axis O x, and there is another axis like O y. Okay, and here O is the origin. Okay, and there is a point P which is at unit distance from this origin, and the on the on the OX axis, and there is a point on Q on the Y point, and this is also at the unit distance from the origin. Okay, now if I say that there is a point A, there is a point A on this plane, there's a point A on this plane, and I want to find the coordinates for this point. For that I have to draw the parallel lines. I have to draw a parallel line, line parallel to OY and a line parallel to OX, as like this. Okay, and a line parallel to OX, and this would give me the coordinates for the point A. Okay, let's say this is point B and this is point C. Okay, now let's say this is the distance from the origin, the point distance OB is alpha, and the distance OC, this is, and the distance OC is beta, not, okay, beta. Okay, this is distance beta. Okay, now the coordinate that I have got are alpha comma beta for the point A. Okay, these are my coordinates alpha comma beta. Now, as you can see that point O, P, Q, what point O, P, Q, these are not collinear. These are not collinear because they doesn't lie on the same line. As these points are not collinear, and if I define the vectors, as this is the line, we can define the vector. So the point P, I define it as the vector S, which is at the unit distance from origin, and the point Q as a T vector, which is at the unit distance from origin too. Okay, so these vectors, these vectors are linearly independent because the points corresponding to these vectors are not collinear. Okay, so as these vectors are linearly independent and they are also passing to the origin, these vectors would form the basis. This will form the basis of R square. Okay, these point vectors S and T would form the basis of R square, and these are what? These are at unit distance from origin, so these are unit vectors. Okay, now if I want to find the vector B and vector C, what did I get? So if I want to find the vector B, so for finding the vector B, we'll multiply its magnitude by unit vector which is in the direction of P. Okay, the magnitude of this vector, this point OB is alpha, so we'll multiply alpha by the unit vector P. Here is the unit vector is P, and the vector P is defined as S. So alpha S, and it is in the direction of P. So okay, so our vector B would be alpha S. Okay, and if I define the vector C, vector C. My C vector would be the if I'll get C vector by multiplying the magnitude of OC by the unit vector which is in the direction of Q. This is my unit vector. Okay, this is in the direction of Q. Okay, so my unit vector, my vector C would be beta T. This is my vector C. Okay, so if I see it ACOB, that's what the plane formed here is. So ACOB, you can see it that this is a parallelogram. This is a parallelogram. So if I define this A by a vector, let's say X. Okay, if I define this A by X, then you can see this that this X can be defined by alpha S plus beta T in the vector form. In the vector form, this X would be alpha X plus beta T. So from this we got that the coordinates of A are unique scalars alpha and beta. Coordinates of A are unique scalars. Unique scalars alpha and beta. So you can see it clearly that this is the, let's say, in the vector form, if this is the vector alpha s, and this is the vector um, beta t, then the then the vector addition of these vectors, this is just a vector addition, then the vector addition of this vector would be alpha x plus beta t, alpha s plus beta t. Okay, and it does form a parallelogram. We have studied this earlier. So from this we got that the coordinates of A are unique scalars. And let's see it. Why are we saying that the coordinates of A are unique scalars? Why are we saying unique here? That we got the unique scalars. Let's see it like this. Uh, let's take another page first. We are saying unique scalars here because if I let's see it in the, if I have three-dimensional Euclidean space. Okay, if I have the three-dimensional Euclidean space, then this is a vector space over R with respect to R. Okay, now there are infinitely many ways to define a coordinate axis with the origin remains unchanged. Okay, now let's say if I define the uh, coordinate axis of the plane as like OX, OY. Okay, these are my coordinate axes where the origin remains unchanged and there is a point A here. Okay, there is a point A here. Okay, now if I'll not change the origin and I'll not change the point, I'll just rotate the coordinate axis like this. These are my new coordinate axes which are passing through the origin. Sorry, this is not. Uh, let's say it is passing through this point. Okay, this is my OX and this is my OY. These are my new coordinate axes. Okay, these are my new coordinate axes. I am just rotating the coordinate axis. Then for this point A, for the coordinate x and y, the previous one, I have the scalars as alpha, let's say beta. And for the new coordinate axis, if I rotate the axis, the new points will be, let's say, alpha dash and beta dash and beta dash. Okay, so for any rotation of original coordinate system gives us a new coordinate system. Let's say for the previous coordinate, let's say for the previous coordinate axis, I have got the coordinates as alpha and beta, and for the new coordinate system, I got the coordinates as alpha dash, beta dash. Okay, so as we rotate the coordinate, we can rotate this coordinate axis in infinitely many ways. Okay, so L we rotate the coordinate, we got the new coordinate system. Okay, and we'll got the new coordinates for the point A. Okay, now let's see it that the unit vectors along the original coordinate axis. Okay, as we have seen in previously that the unit vectors along the original coordinate axis is a basis. Is a basis. Okay, it will form a basis because it is passing through the origin and it has the distance and these are not collinear, so it forms the basis. Okay, so whereas the unit vectors along the new axis, if this is the new axis, let's say it is fine. If this is the new axis, if this, oh shit, my drawing is too bad. Let's draw it more clearly. Okay, this is my previous coordinate, and these are my new coordinate system is like this. Uh, okay, okay, x dash y dash. Okay, so my the unit vectors along the previous coordinate forms the basis. Similarly, the unit vectors along the new coordinate system would also form the basis. Okay, as you can see that there are many angles and there are many ways to rotate the axis, so there are many possible bases possible, even though the dimension remains unchanged. Okay, the dimension remained unchanged. The dimension for three dimensional is 3, so the dimension would remain 3 also, 3 only. But the point you can see that if there is a point here, then for previous coordinates, this will give me the coordinate, let's say here, alpha comma beta, and for the new coordinate system, which is x dash y dash, I will have the point alpha dash beta dash. So we can have as many as bases as many we can rotate the coordinate axis. Okay, better you got it. Okay, now let's see it as I have defined the definition of basis in many ways. I have said that it is the minimal generating set. It is that which where the vectors of subspace can be written in the unique linear combination of the basis vectors. So let's just see them combinedly. So if I say let I have a set S which is the subset of S, where S is subspace of vector space P. Okay, then the following statements are equivalent. Then the following statements are equivalent. How? Let's see this. These are statements, not how. Okay, so A is minimal generating set of S. A is minimal generating set of S. Second is that every element of S can be expressed uniquely as a linear combination from A. Third statement that A generates S and A is linearly independent. Okay. Fourth statement is that A is a maximal linearly independent subset of S. Okay. So if I say that if I have a which is subset of S where S is a subspace, then these four statements are equivalent. A is minimal generating set of S. A is minimal generating set of S. So what does it mean? It means that I require minimum set of vectors which are linearly independent, and those set of vectors would also generate the whole subspace S. This is what we mean by the minimal generating set of S. Okay, and by the second statement that every element of S can be expressed uniquely, as a linear combination from A, as a linear combination from A. This is uh, as that if I have the basis vector, if I have this basis vector, then if I can represent every vector of S in the unique linear combination of this basis vector, then it will give us the basis vector. Okay, so if I can represent every vector in the unique linear combination of set A, then it will give us the basis vector. Okay, A generates S. A generates S and A is Li. That's what we have learned in the definition of basis, that the vectors in the basis would be linearly independent and these should span S, subspace S. Okay. Fourth statement is that A is a maximal linearly independent subset of S. What does it say? it says that if I say that A is maximal linearly independent subset of S, which means that these are the vectors I have to consider all the linearly independent vectors in the subspace S for generating the whole subspace S. Okay, what did I say? That I have to take all linearly independent subspace all linearly independent vectors in the subspace S for generating the whole vector space whole subspace S, because the linearly dependent vectors would also be the linear combinations of these vectors. So I have to consider all the linearly independent vectors, and these linearly independent vectors would be the maximum linearly independent vectors in the subspace S, as I have to consider all the I have taken all the vectors which are linearly independent in the subspace S. Okay, in the subspace S. So these four statements are equivalent. You can say it in any way. Okay, let's see it like this. That if I have a vector space as R square. Okay, and the points are as x1 1 comma 1 and x2 as minus 1 comma 2. Okay, I have 2 points. Then for any point let's say u comma v, which belong to this vector space v. Okay, I can write this point in their linear combination as u comma v is equals to alpha 1 x1 plus alpha 2 x2. Okay, now let's just put the values of these vectors. 1 1 plus uh, alpha 2 minus 1 2. Then alpha 1 minus alpha 2 is equals to u, and alpha 1 plus 2 alpha 2 is equals to v. Okay, so we'll just solve it. Alpha 1 minus alpha 2 is equals to u minus plus, and it would give us 3 alpha 2 equals to v minus u. Okay, so alpha 2 equals to v minus u upon 3. Okay, and alpha 1 equals to u plus v minus u by 3, which is equals to 2u plus v by 3. This is my alpha 1. So the scalars I got, that is alpha 1 and alpha 2, is are 2u plus v by 3 and v minus u by 3. And this is the what? This is the coordinate. I have defined just the coordinates of any point. Let's say A. I have defined the coordinates of any point which belong to this vector V. Thus, we can see that thus every vector in V, this is what the points of the vector, that the every vector in V is a unique linear combination of x1 and x2. Okay, every vector in V is a unique linear combination of x1 and x2, because we have got the scalar as v minus u by 3 and 2u plus v by 3, and also for the different values of u comma v we'll got different scalars alpha 1 alpha 2. So from this we say that every vector in v is a unique linear combination of x1 and x2. So x1 and x2 form form basis of v vector space, because it can be represented, because these vectors can be represented in the unique linear combination. Okay, okay, so now let's see an important theorem, which is replacement theorem. What did it say? Okay, so in replacement theorem, if let's say alpha 1 alpha 2 to alpha n, these are our basis vectors of vector space V over the field F. Okay, and there is a non-zero vector, let's say beta. There is a non-zero vector beta of V. Okay, of V vector space. There is a non-zero vector beta of V vector space, which can be represented in their linear combination, as we know that if there is a vector, this is the basis, and there exists a vector from the V vector space, then this can be represented in the unique linear combination of this basis vector. Okay, that's what we have studied. So beta equals to let's say for the scalars ci. okay, which belong to the field of scalars. So beta can be represented as C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 to Cn alpha n. Okay, then replacement theorem says that if any scalar, let's say any scalar is Cj, if let's say any scalar Cj is not equals to 0, okay, if the value of the scalar is not equals to 0, then alpha 1, alpha 2 to alpha j minus 1, beta alpha j plus 1 to n. This is our new basis of V. This is our new basis of V. What did I did? I said I said that if there exists a vector beta in the vector space V, then the basis vectors of this vector space, then this beta can be written in the linear combination of this vector of these basis vectors. Okay, and if in this linear combination there exists a scalar which is not equals to 0, which is not equals to the 0, then this vector beta can replace replace alpha j. Here I have replaced the vector alpha j. Okay, the vector alpha j. Here beta can replace alpha j in basis. So this is in the replacement theorem. I have vector b. This is represented in the linear combination of the basis vector, and in this basis vectors scalars, I have a scalar whose values is not equals to 0, then I can replace this the vector corresponding to this scalars by our vector beta. Let's see it by an example. Okay, so I have the vector space, let's say R cube. Okay, I have the vector space R cube that contains bases as 1, 2, 0, and another as let's say 1, 3, 1. Okay, and as it is R cube, it has the dimension 3. It has dimension 3. So for this, the standard basis of R cube are E1, which is 1 0 0, E2, which is 0 1 0, and E3, which is 0 0 1. And these are some vectors, and I have said that uh, I want to find the basis vector for vector space R cube that contains these vectors. That basis vectors also contains these two vectors. Okay, let's name it as alpha, which is 1 2 0, and another as beta as 1 3 1. So these vector, let's say alpha, start with alpha. So this alpha can be written in as this is the these are the standard bases of R cube. So this alpha can be written in the linear combination of these basis vectors E1 E2 E3 as alpha equals to 1 E1 plus 2 E2 plus 0 E3. Okay, this is the linear combination here. Okay, so from this we can see that the coefficient of E1 vector is not equals to 0. So, okay, so we can replace the vector E1 by alpha. Okay, alpha can be replaced, E1 can be replaced by alpha. So our new basis is alpha. E2 E3 is our new basis. Okay, and for the beta, so because we have said that alpha and beta are these are the two vectors which contains in the basis, so this is the second vector. So beta, this is our new basis. So this vector beta can also be written in the linear combination of this new basis as let's say c1 alpha plus c2 e2 plus c3 e3. Okay, now beta is 1 3 1, which is equals to C1 1 2 0 plus C2 0 1 0 plus C3, which is 0 0 1. Okay, from this I got C1 equals to 1 and 2C1 plus C2 equals to 3 and C3 equals to 1. Okay, C2 equals to will be 1. I got C1, C2, C3, all coefficients are 1. So beta is equals to alpha plus E2 plus E3. So we can see that the coefficient of E2 vector, coefficient of E2 is not equals to 0. So I can replace the E2 vector by the vector beta. So the new basis would be alpha, beta and E3. This is our new basis. So that's how we can use the replacement theorem. Okay. Now there are some important results. There are some important results for this basis and the dimension topic, which we'll see. Like if I have a vector space V. Okay. If I have a vector space V, V be my vector space of finite dimension. Finite dimension. Let's say n. N. These are some theorems. Okay, so here let V be the vector space of finite dimension n. Then first any n plus 1 or more vectors in V are linearly dependent. Okay, so if I have already said that the dimension is n, it means that it contains n linearly independent vectors. Okay, it contains n linearly independent vectors, and if any there and if in these n linearly independent vectors, let's say v1 v2 to vn, if there is another vector vn plus 1 in this basis, then it would be, this set would be linearly dependent, because there are only n linearly independent vectors. If I add one more vector, then this whole set will be linearly dependent. Okay, and the second thing is that any linearly independent set S, which is equals to u1 u2 to un. Okay, any linearly independent set S, which is equal to u1 u2 to un, with n elements or n components, is a basis of V, is a basis of V. Let's see it. Let's if I have this set of vectors, let's say u1 u2 to un, which has n elements. Okay, now this will form the basis. Any linearly independent set with n components with n elements is form the basis. It has n elements. Okay, and these are linearly independent, and we have already said that V vector space has dimension n, so it will also have n linearly independent set. So we can see it clearly that it will form a basis, because we have taken the set of n linearly independent set, and we have the n linearly independent uh, dimension. We have the dimension n, so these are equal. Okay, let's see it how. So this is the set which are linearly independent set with n elements. Okay, now as these are linearly independent, then the vectors are not 0, then the vectors are not equals to 0, because these belongs to the, let's say, Euclidean space e power n. Okay, as these vectors are linearly independent vectors, then the vectors would not be 0, because if they become 0, then the vectors would be linearly dependent. Okay, now let's, if I define this u1 vector as u11 u12 to u1n. Okay, this is how I define the vector u1. Okay, and from this I consider that u1i, this is the set u1i, that for at least one I, this u1i is not equals to 0 for at least one I. Okay, then this vector u1 can be represented in the linear combinations of the standard basis vector. We have standard basis of e's power n as e1 e2 to en. Now we can represent these vectors in the linear combinations of the standard basis as u11 e1 plus u12 e2 to u1n en. And by using the replacement theorem, the coefficient of, let's say, the coefficient of e1 vector, which is u11, is not equals to 0, then I can replace vector e1 by u1. Then my new basis would be u1 e2 to en will be the new basis, will be the new basis. Okay, similarly, again let's consider that the second vector u2 which is not equals to 0. Okay, this vector is not equals to 0, as our new basis is u1 e2 to en. Then this u2 vector can also be represented in the linear combinations of this basis vector. Let's say for the scalars theta 1 theta 2 to theta n. Okay, then u2 can be represented as theta 1 x u1 plus theta 2 e2 to theta n en. Okay, for theta let's say, okay, sorry. So we have represented u2 in the linear combinations of these basis vector. Okay, now if I say that the theta 2, the coefficient of theta 2 is not equals to 0. Okay, then I can replace the vector e2 by the vector u2. Then the new basis would be u1 u2 e3 e4 to en will be the new basis. So proceeding similarly, so by proceeding similarly for u1 u2 u3 to u4 to un, we got that the vector u1 u2 to un is a basis of, let's say, is power n. Okay, is power n. Okay, so any linearly independent set S equals to u1 u2 to un with n elements which are linearly independent is a basis of V. Okay, okay, now the third statement here is that any spanning set, any spanning set, any spanning set T equals to v1 v2 to vn, where these vectors these all vectors belong to the vector space V. So these vectors belong to the vector space V. So any spanning set T of V with n elements, with n elements is a basis of V. Okay, so it is easy to see that if I have a spanning set with which has n elements, and it has already given the dimension is also n, that the dimension is also n, then uh, it means that if the dimension is n, that it means that it contains n linearly independent set, that it contains n linearly independent vectors which generates the whole vector space. And it means that if I have a spanning set of n vectors, n elements, then it will generate my whole vector space, it will generate my whole vector space. So these statements are very easy to see, but there is one thing to note here, that here I have already defined that the dimension is n. If I haven't defined this, that the dimension is n, then there are some possible cases for that. Okay, but here I have already given that the dimension is n, then we can easily see that if I have the dimension n, then this dimension n means that there are n linearly independent vectors. Okay, and there are n vectors which generates the whole vector space S. So this is what we have said in the second example and the second statement, and in the third statement, that I have n linearly independent set that would generate the vector space, and if I have any spanning set which has n elements, that would also generate the vector space. And in the upcoming theorem, we'll see you will see it clearly what I mean by defining the dimension and beforehand. Okay, so let's continue it in the next lecture. For today it's sufficient. Thank you.